oxide. You see, for group 1 elements, they can form 3 types of oxide. Either ordinary oxide, which its oxygen, its oxidation state is -2, or they can form peroxide. In that case, oxygen show oxidation state of -1, or superoxide, which the oxidation state of oxygen is -0.5. Lithium cannot form peroxide, neither can it form superoxide. So it forms only one type of oxide, which is the normal oxide. That one, the oxygen shows the oxidation state of -2. So on combustion, lithium combines with oxygen to form lithium oxide. And when you calculate the oxidation state of oxygen, it will give you -2. It cannot form peroxide or superoxide, where the oxidation state of oxygen will be -1 or -0.5. So let me illustrate that one for you to see something. So let's see, this is lithium oxide. So now the oxidation states of the compound, since the compound carries no charge here, means the whole compound, its oxidation state is 0. And how do we come by it? As we did last time, the total oxidation state of lithium plus that of oxygen should give you 0. So now we already know that lithium is in group 1, and all group 1 elements have fixed oxidation state of +1. So we have 2 atoms of lithium, and therefore we are going to get 2 times +1, that will give you +2. And oxygen in its normal oxide show oxidation state of -2. So we have only 1 atom of oxygen. So when you add, so +2 -2 will give you 0. So this tells us that the lithium, the oxygen here is showing oxidation state of -2. So lithium can form only oxide of oxidation state of -2. But let us take this compound. Sodium peroxide. And there is a chemical formula for sodium peroxide. So here, what is the oxidation state of oxygen here? We now know this one is the fuel compound. So once there's nothing here, means the oxidation state of the compound is 0. So the total oxidation state of sodium atoms and oxygen atoms should sum up to give you 0. So here, sodium is in group 1, and therefore its oxidation state is +1. So how many of the sodium atoms do we have here? 2. So we are going to get +2 oxidation states. Now, minus, here we assume that we don't know the oxidation state of oxygen here, and therefore it's going to be 2 times X. Everything should give you 0. So when you solve for your X, it's not going to be 2x. Here we don't know, so here should be plus. So it's not going to be 2x is equal to -2. Well, we are taking all this number without any any element on it, or this one doesn't have any variable. So when it crosses the equal sign, it tends to be negative. So we have now group like terms. Now, if you want to get our x, are we not dividing 2 by 2? So when you divide 2 by 2, you're going to get your x being equal to what? -1. And what does the x stand for? It stands for oxidation state of oxygen, which we don't know. So we have now found the oxidation state of oxygen to be here -1. So in peroxide, oxygen is showing oxidation state of -1. And what we are saying is lithium cannot form this state, this type of oxide. It is only sodium and potassium that can form. So that's why we are saying that the lithium has different properties from other group members. So one of the properties of lithium, which is different from other group members, is its oxidation states. It's not able to form peroxides, but it's able to form an oxide that has the oxidation state -2. So lithium differs from all the one element because it cannot form peroxide or superoxides. Okay, then lithium nitride is formed by direct combination with molecular nitrogen. So if lithium can also react with nitrogen, lithium carbonate and phosphate are less soluble than the rest. So here lithium can easily combine with nitrogen. So we are now listing the properties of lithium, which others do not have, other group 1 elements do not have. One of them is the oxide that it forms. It only forms one type of oxide, which is the one that's oxygen show oxidation state of -2. Then it can also form a compound with nitrogen direct. This give you lithium nitride. Then it's 8 carbonates. 8 carbonates is less soluble in water. But all the one elements, their carbonates are soluble in water, like sodium carbonate, potassium carbonate. They are all soluble in water. But lithium, the type of carbonates, when you have lithium carbonates and lithium phosphates, they are less soluble in water. So their other oxides are this. Lithium can also form oxides, which is the same as all the other elements, in the group 1. What are the uses of lithium? It is
So please,
yeah.
with the reaction, we are looking at the reaction of lithium, but point 3, you see that it is written that but sodium, at meanwhile we are talking about
This point 3.
the other one we have, but
Point
you
3
have
is lithium nitride is formed by direct combination with molecular nitrogen. So why is the other point 3? Why is it the point 3? I'm listening to you.
so scroll down.
What are you referring to?
We have when we were talking, I saw some point there, point 3, another point 3 before this one.
This one.
No, sir, go
I should
up.
go back.
Yes.
This one.
This one.
uh, This
But
one. This one is just what I've just explained. We are, you look at this point.
on combustion forms. Okay.
You read this place. What is there?
Lithium
Lithium
differs from its group members in the following ways.
in the following ways. So one first way is what?
On combustion forms and
On
oxide.
combustion, on
Forms.
combustion forms and oxide. So there is the combustion of the oxide that has formed. But it's now using this point 3. So this is not part of this is here shouldn't be 2 and here shouldn't be 3.
Okay.
Here should be 1. Then the next one, this is yours. Here should be 2. Is that okay?
Okay.
And here
Okay.
should be 3. He was just using this to explain. So we are talking about combustion. So here should be an example of combustion. Are you not combining lithium with oxygen?
Yes.
And the oxide he's talking about. And he's saying that this is the only type of oxide that lithium can form. But when you come to this, he was now explaining this type of oxides. This one is peroxide. That is formed by sodium. So sodium can form ordinary oxide. It can form out to peroxide. Is that okay? Then potassium form all the 3. So lithium cannot form. That's why you made this one. So here shouldn't be 3. Okay.
Okay, sir. Thank you.
Another one that makes lithium different from other elements is lithium nitride is formed by direct combination with molecular nitrogen. Other members cannot form their sodium nitride or potassium nitride by direct combination nitrogen molecule, but lithium can do that. So countries are others, they form that nitride in direct combination, indirect. Then the next point is we cannot get lithium carbonates or lithium phosphate. And we are saying that all group 1 elements, their carbonates, their sulfates are all soluble. But when we compare the solubility of lithium carbonates and lithium phosphate to that of sodium and potassium, lithium 1 is less soluble. Then we go to the next point. All group 1 elements, their oxides are basic. So lithium also form the basic oxides. And when it combine with in water, it will result into the first thing that I indicated to you. It is so lithium hydroxide. Now, uses of lithium. So it can lithium in water, it form a base. So lithium oxide, what is formed, is used to purify vehicles and submarines. Because why? It can easily react with carbon dioxide. Now, so you want to purify air. Vehicles, they are put in vehicles. People sit in the vehicles, we generate carbon dioxide. So in order to remove the carbon dioxide, lithium oxide can easily form a compound with carbon dioxide. And that one is less soluble. So in vehicles, this lithium oxide are used as purifier. So there is a chemical reaction that's denoted. Lithium oxide plus carbon dioxide you form lithium carbonates plus water. So this is telling us the materials in which it can be used to purify. So we have airplane, submarine, we have vehicle, or lithium can also combine with molecular hydrogen at high temperature to yield lithium hydride. And that is also the illustration. So here, hydrogen is showing oxidation states of -1 because lithium is losing the electron and being taken by hydrogen. Now, when you form lithium hydride can also react with water to also give you lithium hydroxide and hydrogen gas. So if you form your lithium hydride and you go and put it in water, it will dissolve to form a basic solution and evolution of hydrogen gas. So if it can absorb water and any substance that can absorb water, what do you call it? You call it a drying agent. So lithium oxide is used as a drying agent for organic solvents. So when you prepare organic substance and you want to dry them, you put this lithium oxide in there, and you'll be able to get your substance drying. So this is what we see here. Then lithium can also form a compound with aluminum and hydrogen, what we call lithium aluminum hydride. And this one is very powerful reducing agent in organic synthesis. During the organic preparations, you use this one to prepare a lot of organic substances by using lithium as reducing agents. Maybe you can use it in the preparation of carbonyls and other things. It is used as a reducing agent. Then lithium chloride, lithium bromide are highly hygroscopic. Now, what is a hygroscopic substance? Hygroscopic substance can absorb water, but they will not dissolve in it. The liquescent substances absorb water and dissolve in it to form a solution. So lithium chloride, lithium bromide are highly hygroscopic. They have greater tendency to absorb water. So if you want to humidify compounds, like in the air condition, it is put there and it will remove moisture. So hence used as a dehumidifiers and in air conditioners. So we have the air condition there. So what is put in there to absorb the water in the air condition is lithium chloride or lithium bromide. Then how do you use the lithium carbonate for? Lithium carbonates are used in drug formulation to treat manic depressives. So we have these components in human beings, and in order to suppress it, you use lithium carbonate. So when you go to the hospital and you are showing signs of aggression, emotions, endocrine responses, feeding, reproductive behavior, social, all this stress coping. Now, if this, you have this in your system, these are some of the things it's going to give you, and therefore you use the lithium carbonate to suppress it. So in excess of this compound, serotonin What does the serotonin do? Now, bone health can cause osteoporosis when levels are too high. So some people, they have pains in their bones. So if this one is too high in the body, and what do you do to control it? We use lithium carbonate. Clotting of blood helps body to heal faster. You need them, but when they become too much, it also have 8 causes or 8 symptoms. They can affect the body, and therefore they needed to be managed. So what are the things that this chemical can do for the body? Without it stimulates sleep, stimulate the area of the brain that are in control of sleep-wake behavior. And look at another importance of sexual function can cause decrease in libido when levels are too high. So when the level of serotonin is too high in the body, your sexual urge goes down. So how do we rectify that? And we use lithium carbonate.
Sir,
If the level is also too high,
sir,
what happens? Yes.
please, the serotonin, are they also hormones in the system because of the
Yeah,
function or the
one
way
of
that
the hormones body system.
Okay, okay, sir.
So it has it should be in the body for certain things to function very well in the body. Why? If it is not there, your blood cannot clot.
Okay, okay.
Now, if there is a cut and your blood cannot clot, can the wound be healed? No.
No, sir.
So healing of so when you have the cut, don't you say because of the blood can clot, don't you see some healing process that begins? If the cut is so small, you can easily see it without even putting any medicine there. It's as a
Yes.
result of clotting of the blood. And this is one of the hormones that control it. So
Okay.
in our body system, we need it. But when it becomes excess, it also gives different symptoms or feelings that is also not good in the body. One of them is emotions. So some people don't say they are too emotional. In this like say this they cannot stand it.
Yes.
You see that some people, they are so aggressive. They become so aggressive. They become so stressful. In this slightest and they become stress off. And we need to control the amount in the body. And therefore, what do you use to control that? You use lithium carbonate.
Okay, sir. Thank you.
So what can these hormones, what can contribute to this hormone that we just talking about, serotonin deficiency? When the body needs it, and so if you become too anxious, then aid levels goes down. When you become so worried, panic, phobia, mental obsessions, depression, a lot of them, pain, sleep cycle disturbances, all these things will affect it, and you need to have a chemical that will manage it for you. So we've learned a little about lithium, its behavior, the compounds that it can form, that is in terms of the reactions. So we are now looking at sodium 2. Now sodium is also part of the group 1 elements. So sodium, what can we get from the sodium? The nature, sodium is salt. The color, slavery white, highly reactive metal. It belongs to metal that we describe them as alkali, and it belongs to group 1 in the periodic table. Now, potassium and sodium are, when you compare the amount of potassium and sodium in the seawater, the seawater contains higher amount of potassium than sodium. Potassium is essential to plants and not sodium. The ratio of sodium to potassium is 28:1. Why? Because the potassium is so essential to plants and animals. Plants easily absorb them when they are in the system. So in the seawater, we have a lot of sodium in there than potassium. Look at the ratio, 28:1. Now, common names and the formula for compounds that contain sodium. We have the common one, formula is sodium NaCl, and where it is found in the rock salts, halides. Then we have the chili saltpeter, which normally we call it a tone. So the chemical formula is NaNO3. Then Sevites, KSC. Then we have abites, autoclaves, human. All these are their chemical formulas. How is sodium obtained? It is obtained by electrolysis. So we use what we call down cells. So on the down cell, we have the electrons, positive and negative electrons. So if you want to obtain your sodium, we need to convert it into the molten form before we can extract the sodium metal. So what can help us is by using calcium chloride. Calcium chloride, you combine with sodium chloride, and it can easily be melted at the temperature of 600 degrees Celsius. And other than that, if you want to melt sodium chloride itself, we need a temperature of about 800 degrees Celsius. By combining it with the sodium chloride, the temperature is reduced to 600 degrees Celsius, and therefore sodium can be changed to solid to a molten form, semi-liquid. Then in the molten form, when the electricity is passed through, what is going to happen? Now look at in the machine, we have the anode and we have the cathode. So we have the carbon anode and the iron cathode. So the anode is positively charged and the cathode is negatively charged. So when the sodium chloride is in the molten form, it stays as ions, sodium ion and chloride ion. So in the when electricity passes through, it separates and sodium migrates towards where the negative charge pole. Then the chloride migrates to the positive side. So we are going to get carbon anode. Then, so at the carbon anode, what is going to happen is the chloride ion will lose its electron, or it will accept the electron and become a molecule. Where at the cathode side, we have excess electrons there. So sodium, that is Na plus, will take electron from the cathode, which has excess electrons, and it will reduce to sodium metal. When we go to the anode side, there is deficiency of electrons there, and therefore chlorine will give its electron to that pole and you form the chlorine compound. So let us see the illustrations here. Okay, so when you look at this, okay, let me clean this sheet. So when you take in the molten form, this is what we are going to see. We have our sodium chloride like this. We have our sodium chloride like this. So if it is in the molten form, we assume that it is aqueous. So what is its state now? Sodium now becomes Na plus. Then the chloride becomes Cl minus like this. Now, so the anode plates, if we take this to be our anode plate, or the anode side, then this one becomes the cathode side. What we are saying that this one is cathode because it has excess electrons. This one is anode because it has deficiency of electrons. So it is positively charged. Now, sodium, what is Na plus, indicates that it has this deficiency in what? Electrons. And therefore, when it comes to the pole that contain, when it comes closer to this pole, what is cathode, has excess electron. So the excess electron, sodium will attract it. So what is going to happen? It's now going to get a complete, and it will be reduced to sodium. So reduction is taking place at the cathode. So sodium, what is positively charged, comes to the cathode. Cathode that has excess electron will give its electron to sodium, and sodium will be reduced to sodium metal or sodium atom. Then when chloride, what is negative charge, has excess electron. So this excess electron that it has, because this pole is positively charged, is now going to donate the electron to the pole, and therefore it is now going to remain from this chlorine molecule. Chlorine molecule like this. So what do you observe during this process? During this process, you get to know that chlorine has formed at the anode because there will be effervescent or production of a gas coming out from this pool. So when the gas is collected and tested, it proves to be a chlorine gas. Then at this cathode, you will see precipitate that will be forming around it, or precipitate will be falling off from the cathode, and that one becomes sodium. So this is what takes place. This is about the electrolysis. So in the electrolysis, it is just passing electricity to separate ions in solution. So when you look at the machine, this device, so this is the device, and the name of that device is what we call the down cell. So in the down cell, you connect this, it has electricity source, and the electricity that is going to pass through this molten ions, and when it is passed through the molten sodium chloride, it's going to separate it into chloride ions and sodium ions. The sodium ions, as I've just explained, will migrate to the cathode, take electron, and they will be reduced to sodium metal. Then the chloride ion go to the anode, give their electrons to the anode, and they will be reduced to chlorine molecule. So that's how we are able to produce sodium metal. First, the extraction goes by getting your sodium chloride, combining the sodium chloride with calcium chloride, heating to the temperature of 600 degrees Celsius, then using electricity to pass through it to separate the ions from sodium from chloride. So that all the sodium ions will migrate to the cathode to be reduced to the metal, and all the chlorine ions will also migrate to the anode to produce chlorine gas. Now, the same procedure that is used to obtain sodium is the same procedure that will also be used to obtain potassium. But for potassium, if you have a potassium salt, like sodium potassium chloride, through the electrolysis, you can also take your sodium. So electrolysis method is not appropriate because potassium will float in the cell and vaporize into air. So how do we get our potassium? It is extracted by distillation of potassium chloride in the presence of sodium vapor. So if you want to produce potassium, you don't use method of electrolysis. But what do you do? You use method of distillation. You distill potassium chloride in the presence of sodium. So quickly, sodium will go and bond with chlorine to form sodium chloride. Then potassium will be obtained as a gas. And this reaction takes place around 770 degrees Celsius. So all these another processes of what the extraction. All what I was describing is the simplest from when you gotten it, because these minerals, these ores are in rocks. So you go and take the rock, you nail it, then you mix it with calcium sulfate, which we call calcination. Then we continue to nail it before we come to the proper extraction. So extraction of potassium and the mineralization. Here you also pump in carbon dioxide water, you filter the potassium sulfate, then you filter. So the extraction by using the electrolysis is the last stage. After you've now been able to get converts everything in the ore and you get the final stage. So when you get to the final stage, the last thing to do is use the method of electrolysis to obtain your pure metal. And this is the machine that depicts it. So all these processes is what you have been reduced to what I was trying to tell you. So here we have the portion of the machine that will take the rocks. You have a portion that will mill it. You have a portion that will add the calcium sulfate to it, calcination, then all this process goes on. So look at how the whole thing is done. What are the uses of sodium and potassium? Sodium and potassium are very essential for living matter. So sodium and potassium are essential for living matter element. They are present in a lot of things, including intercellular and extracellular fluids, which influences osmotic and enzyme function. There is some level of osmosis that takes place within the organisms, living organisms, including plants and animals. Now you can see that plants absorb water from their root hairs, and that's one is not the method of osmosis. Now you assess how the water gets into the cells and the sugar and those kind of things. Those things are as a result of balance and the osmotic pressure. Now your body becomes dehydrated. When your body cells lose water, your body becomes hydrated. When the body cells absorb more water, but they should be in balance. So when the blood sugar is so high, through osmosis, water will be lost from the cell to reduce the sugar content. And when the sugar, the cells also lose more water. Water must also move from the blood into the cell. So all these things are done by the principle or process of osmosis. And therefore, what chemical controls it? Sodium and potassium are the chemicals or elements that influence this osmotic pressure or osmotic processes in living organisms. Okay, so you can see that sodium and potassium are very vital for living organisms. What is the source of sodium into the man's or in the living organism like man? We get our sodium from the common salt that we take, sodium chloride. We can also get sodium into the system by sodium carbonate. A lot of food contains sodium carbonates. So this illustration is telling us this exchange. So sodium, potassium pump here. We have the cytoplasm, we have the ATP, so the movement, then we have the extracellular fluid. So exchange of these minerals is by the influence, the enzyme and function of this area is as a result of what? The osmotic that is being experienced here. And this experience comes into being as a result of exchange of sodium and potassium within this. So if you don't have those ions there. When the enzymes and whatever have you get to this place, they cannot be transported or they cannot be exchanged. So for industrial process, we have sodium carbonate for industrial process, where in the baking of bread and those kind of things, we also need them in the water treatment, manufacturing of soap, food additives, detergents, and medicine. Because if we are producing soap, we need sodium. Where do we get our sodium? Get it from either sodium chloride or sodium carbonate. That's why you go and buy the caustic soda, the preparation of soap. Salt is used as additives. It's also used as salt to preserve food. Now, what reactions can these elements undergo? Both potassium and sodium are more reactive. They both react with cold water to form hydroxides, and they give out hydrogen gas in the limited amounts. So we are now going to, if the oxygen is in limited amount, the oxide that will be formed will be sodium peroxide, which I've already illustrated it for you. So in limited oxygen, sodium yields oxides, and in excess, we get peroxides. Potassium reacts for oxygen in limited amount to produce the peroxide, and in excess, it gives you peroxide. So let us see the chemical formula for. Okay, let us look at this. Now, we have our sodium. So we are saying that limited amount, limited amount. We are going to produce sodium oxide. Here's what we are going to produce. Limited amounts, we produce sodium oxide. But if it is the oxygen, the amount of oxygen is in excess, means you have excess oxygen. Oxygen in excess. Instead of producing sodium oxide, you produce sodium peroxide. So there is a chemical formula for sodium peroxide. So in the limited amount, you produce sodium oxide. By in excess, you produce sodium peroxide. Then when it is potassium, in limited amount, you produce potassium peroxide. In excess, we produce potassium superoxide. And this is a chemical format for superoxide. So here, when you find the oxidation states of oxygen here in this, if you see that it will give you -half. Here, the oxygen here will -1, and here the oxygen will -2. So we now come to realize that we cannot form lithium peroxide under the normal condition. We can only form one type of oxide for lithium. We can, when you go to potassium and sodium, we can form peroxide and superoxide. We cannot form superoxide with sodium, but you can form superoxide with potassium. Okay. So this that I've just explained. So in limited oxygen, sodium US oxides, and in excess, we get peroxides. Potassium reacts with oxygen limited to produce peroxide, and in excess, you produce peroxide. So this is the general formula. So we have monoxide, peroxide, and superoxide. There are three different types of oxides that with one element can form. So when the metal form monoxide, it is using oxidation state of -2 of oxygen. If it is forming peroxide, that metal is combining with oxygen, and here the oxidation state of oxygen is -1. And if it is peroxide, it is -half. So these are the three oxides that metals with one can form. So these are examples. Now, what do you see? Sodium metal reacting with oxygen. Oxygen in excess. So we have peroxide. Potassium with oxygen. Oxygen is limited. We shall form peroxide. When oxygen is in excess, this one will give you potassium peroxide. Okay. Now, when the oxides are based with one element form, and you put them, they are soluble in water. So sodium peroxide in water will give you sodium hydroxide, which is the base. And there will be, so when you have sodium peroxide and you put it in water, you are going to form sodium hydroxide and hydrogen peroxide. But it won't be in the form of gas in aqueous. And you've not seen hydrogen peroxide before. Most of you have used it before. When you have problem with the teeth, you go to the drugstore and buy hydrogen peroxide, and this is what you see here. Now, potassium peroxide also dissolve in water to give you potassium hydroxide, oxygen, and hydrogen peroxide. So let me ask you a question. How will you prepare or produce hydrogen peroxide from any of the oxides? So for you to prepare hydrogen peroxide, you either use go sodium peroxide or sodium superoxide or potassium superoxide. When you dissolve sodium peroxide in water, you produce your sodium hydrogen peroxide. Or when you dissolve potassium peroxide in water, you produce your hydrogen peroxide. But here, you produce your base solution, and there will be evolution of oxygen gas if you are using superoxide, potassium peroxide. So in breathing equipment, what they normally put in is potassium superoxide. Well, they know when it comes in contact with water, it's going to release oxygen. So because of oxygen generated in piston 5, it is utilized in breathing equipment. And this breathing equipment that you see. How do you produce sodium bicarbonates? Sodium carbonates. When you have your ammonia and you react ammonia with sodium chloride, you fair and in presence of hydrogen carbonates. So we have our hydrogen carbonates, sodium chloride, and ammonia. You are going to produce your sodium bicarbonates and ammonium chloride. Then you continue with this. The sodium bicarbonates will be converted to sodium carbonates, carbon dioxide, and water. So after you produce this, you isolate it, heat it, and the hydrogen will form water with one of the oxygen atom, and carbon will also be produced. Because of cost of ammonia and the pollution issues, this method is no more in use. So if you want to prepare sodium carbonates, because ammonia is very expensive and it also generates a lot of pollution, you don't use this method of combining ammonia with sodium chloride to produce sodium carbonates. In the current method is of crushing and heating. So you go for the rocks that contain sodium carbonate, sodium hydrogen carbonate, and water. And what do? You heat it, and all the water will be converted, will vaporize. Then carbon dioxide will also generated. What will remain as solid will be as sodium carbonate. Now you have produced your sodium carbonate in this form, but it's not accepted. They think it still contains some impurities. So you dissolve it in this method of crystallization, the generator of sodium carbonate. Remember, when you produce the sodium carbonate, it is soluble, and therefore we can use method of crystallization to make it pure. And this one is US which produce so much of it. Now, what is sodium hydroxide and potassium hydroxide? They are all known as strong bases. They are all soluble in water. They are produced by electrolysis of potassium chloride and sodium chloride. So when you electrolyze potassium chloride and sodium chloride, remember, you are dissolving the thing before you can get this one to be in the ionic state. So the potassium will be converted to a potassium hydroxide, and sodium will be converted to sodium hydroxide. Sodium hydroxide is used in many ways. One of the ways is the preparation of soap. So it's used in making soap and organic and inorganic compounds. Potassium hydroxide is also used as electrolyte in batteries. And it's also used to remove carbon dioxide and sulfate from air. So when potassium hydroxide, if you want to purify the air, you go for potassium hydroxide because when it is there, it absorbs carbon dioxide to form potassium carbonate. Then you can also absorb sulfur to form potassium sulfate. In preparation of gunpowder, what do? You go for potassium nitrate, what we call wood charcoal, and burn it with sulfur. So sulfur plus carbon plus potassium permanganate is going to give you an explosion. And this is what we use in the gun. So gunpowder comes with fire, we fire it and produce this. Now, so we have a lot. So in the group one, we have looked at lithium, potassium, and sodium. And all these characteristics that we are talking about is common with the group members of the metal. But because cesium, francium, and rubidium are so reactive, that's why we are not wasting our time on them. Now let us shift on to the alkaline earth metals. What are they? They are group 2 elements. So group 2 elements, the first one is beryllium. But beryllium is not so much classified as metal, so much metallic, because it can form covalent bond with other elements. So you look at magnesium, calcium, strontium, barium, radium, they are the proper two metals. So all the two metals also undergo the same type of reaction of one element. So we shall look at their reaction of oxygen, water, acid. Their oxides, does it form acid or does it form hydroxides? And their halogens and those kind of things. Okay, so when you burn the two members in air, what do you see? So they form the oxides of their metals. So when you burn the two members, you form magnesium oxide, calcium oxide, and so forth. Now, if you want to, they are also extracted by the electrolysis. So their oxides could be in the form of the ore. You go for the ore. If you want to extract, let's say, magnesium, you combine magnesium oxide with calcium oxide and iron silicate. When you heat to the temperature of about 1450, you'll be able to break down to get your magnesium. But one other way of getting magnesium also reacting of HCl with magnesium oxide to get magnesium chloride. Then use method of electrolysis to separate magnesium from the chloride. And these are their percentage composition in the earth crust. If you want to extract beryllium, then you go for beryllium fluoride. You will react it with magnesium. Magnesium remove fluoride because more reactive than beryllium, so that you get your beryllium and form your magnesium fluoride. If these ones, if you want to also get calcium, you also go by this. So let us see about the beryllium. Beryllium is a relatively rare elements in the universe, usually occurring as a product of larger atomic nuclei that have collided with cosmetic rays. Now, We now know the electron affinity, electronegativity, ionization energy, and so forth. Now, why do we say beryllium exhibits more metallic property than metal? Now, let us look at the ionic energy or ionization energy of beryllium. When you go back to the electron configuration, now beryllium has atomic number 4. So when you draw the electron configuration, you're going to 1s2, then you have 2p2. Now, the valence electrons are made up of 2 electrons. So here become 1, and this case become another. Now, since within the group, this one has only one second energy level. When you move on to, let's say, magnesium, and you draw its electron configuration, I think magnesium has atomic number 12. So its atomic configuration is 1s2, 2p6, 3s2. Then you go to your 3p1, 3p2 rather, 3p2. So when you look at this, we can easily see that beryllium has 2, principal quantum number 2, means its electron is in the second energy level. Now, when you come to, let's say, magnesium, which is also in the same group, its valence electrons are in the third energy level. So when you look at the beryllium, can't you see that now the shielding effect between principal quantum of the second energy level is closer to the nucleus than the third energy level. And look at the number of electrons that exist between them. Now, for the first energy level, it has only 2 electrons. But when you come to the second energy level, the total number of electrons between the nucleus and the third energy level is going to give you a total of 8. So we are now saying that because of this, the electrons, inner core electrons in magnesium are more than the inner core electrons in beryllium, thereby acting like a screen. So we call it screening effect. These 2 electrons in the second energy level, they are all being attracted towards the nucleus. But because of these 2 electrons in the beryllium, the screening effect, or in other words, the opposition force that is preventing the nucleus to attract the valence electrons are less as you compare to magnesium. So we say that magnesium, because it has 8 electrons, its screening effect is greater than beryllium. Screening effect, the electrons in between the valence shell and the nucleus are acting as a screen to block the attraction of the outermost electron towards the center. So this is now telling us that beryllium, whose has weak screening effects, the two electrons in the 2p orbital is more attracted towards the center than magnesium. And therefore, for them to lose energy, you need higher amount of energy for it to cause an electron to be lost in beryllium as you compare to magnesium. So the ionization energy of beryllium is higher than that of the other members in the group. And when you have higher ionization energy, you are getting closer to your non-metals because you need to be ionized before you can form a compound. So if the metal needs so much ionization energy for it to cause an electron to be lost, then it prefers sharing electrons to form covalent bond than forming ionic bond. So beryllium is comfortable forming covalent bond with nonmetals than forming ionic bond. So beryllium chloride is covalently bonded as you compare to magnesium chloride, which is an ionic bond. And this comes as a result of a weaker screening effect in beryllium as we compare to my other members in the group. Okay, so let's go back and see. So that is what has been shown here. Beryllium has a higher second ionization energy as compared to the rest. This is as a result of 2x is only shielded by 1x. Means the second energy level has only 1s orbital in between. But when you go to the rest, they have more than 1s orbital. Also, the energy required to promote electron to form sp hybrid orbital is convenient. Hence it forms covalent compounds. So beryllium form covalent compounds. Despite the fact that it is made with in group 2, because we think it should form ionic compounds. So beryllium hydride, beryllium chloride, and beryllium bromide, they are all covalent compounds. So this it is formed. If you want to form beryllium oxide will react with carbon tetrachloride to give you beryllium chloride and carbon dioxide. Now, beryllium also, a deliquescent substance absorbs water from the surrounding air and eventually forms liquid. This is what I've also already told you. So what are the main ore in beryllium? This is what you see, beryllium. How is it extracted? Ore is converted to first beryllium oxide, then later converted to fluoride. the fluoride is then heated to a temperature of 1000 degrees Celsius. So we've now converted our beryllium ore to the oxide. Oxide has been converted to beryllium fluoride, and you heat it, you react it with magnesium at the temperature of 3000 degrees Celsius, and you produce your beryllium. Beryllium is highly toxic when you heat. When you inhale beryllium in your system needs magnesium. So when beryllium goes into your system, it's going to compete with magnesium, and that will bring about poisoning your system. So beryllium is highly toxic. When beryllium ions compete with magnesium ion at the enzyme sites, and therefore what your body is supposed to do will not get that one. So deficiency in magnesium, what is it going to cause? You cannot sleep. You easily get fatigue. You get migraine, depression, high blood pressure, excess stress. You become restless. Your legs become restless. Then you have muscle cramps. So this is what is going to deficiency in magnesium is what is going to kill you. So it is not the beryllium that is going to kill you, but the deficiency. And what element is going to cause that deficiency is when the beryllium is there. What do you use beryllium for? As an alloy in copper to enhance hardening. So if you want to harden copper, you add magnesium to it, beryllium to it. Window in X-ray tube, it does not absorb high energy radiation. So X-ray tube, the window, is made up of beryllium. And why? It does not absorb high energy of radiation. It is used as a moderator in neutron, when you want to, as a moderator of neutron produced in nuclear reaction. When nuclear reaction goes on because of bombardment of the neutron with an atom. So if you have a system that can check the neutrons, means that nuclear reaction can come to a halt. And what do you use to control the excess nuclear reaction? We use beryllium. So it is used as a moderator in lithium or in nuclear reaction. So then we are magnesium. What are the magnesium? Do they have any importance? Magnesium is an important mineral, playing a role of over 300 enzyme reactions. So without magnesium, most enzyme reactions cannot take place in human beings. So if you say that our body needs magnesium, very, very important to our body. Okay, so these are the nutrients or the fruits that we can get, fruit and nut that we can get magnesium from it. When you eat banana, you have a lot of magnesium there. We have pear, we have lettuce and all other things, cabbage, granules, dates, and all sorts of things. We can also get them in capsules or tablets. Now, inadequate intake. We have, for every diet, we have the recommended amount. So recommended dietary allowance for magnesium. And you look at the age. Somebody, a child to about 6 months, what is the amount of magnesium that that child needs? If it's a male, you need 30 milligrams. If it's a female, 30 milligrams. Now, between 7 to 12 months, what is there? The female needs 75 milligrams there, and the male 75. Between 1 to 3 years, 80 milligrams for both sexes. 4 to 8 years, 130 milligrams both sexes. 9 to 13 years, amount of magnesium that the body needs is 240 milligrams for both sexes. Now 14 to 18 years, for male 410, female 360, pregnant women 400 milligrams, and then lactation mothers 360. 19 to 30 years, men 400, women 310, pregnant woman 350, lactating women 310. 31 to 50 years, men, we need about 420 milligrams. Women, they don't need it too much, 320. And 360 for pregnant and 320 for lactating. Now, 51 years plus, male 420 and female 320. Now, magnesium is the least plentiful element on the earth crust. It's about 2.5 by mass. The main source is from seawater. And this is the ores that we can get magnesium from it: brucites or milk of magnesia, dolomites, epsomites. So these are where you can get our magnesium from. What reactions does magnesium undergo? Because it's not so reactive as group 1 elements, it does not react with cold water, but it reacts with hot water. When it reacts with hot water, you form magnesium oxide and hydrogen gas. How does it burn in air? It burns brilliantly in air to form magnesium oxide. Then it also reacts with nitrogen direct for you to get magnesium nitride. Possibly because of there is the presence of air in the atmosphere, and the air contains the nitrogen. That's why it may be able to combine with nitrogen. This property of magnesium makes it very useful in photography and flower. What do you use magnesium for? It is light, so it is used for light structural metals, alloys. It is used as a cathodic production in batteries. It is found in green pigments doing photosynthesis. Magnesium ions are essential for plants and animals. Barium hydroxide is amphoteric, means it can behave as acid and base. So calcium. Calcium is a mineral that is necessary for life. In addition, what do we get from, what is the importance of calcium? It builds our bones, building of bones and keeping them healthy. Calcium enables the blood to also clot, our muscles to also contract, and our heart to also beat. About 99% of the calcium in our bodies is in our bones and teeth. So we now know how important calcium is in our body. Without calcium, our heart cannot beat. Contraction of muscle, clotting of our blood. Now, what are the organic components that we can get calcium from? You can get it from a lot of things, as you see, a lot. Watermelon, beans, what have you, a lot, nuts. In the earth crust, the calcium is there in the form of ore. We have calcium carbonates, magnesium carbonate. So calcium carbonates, which we refer to as chalk or marble or limestone, calcite. Then it is also in dolomites, gypsum, fluorides, and then in quicklime, which is calcium oxide. So all these are examples of ores that we can get our calcium from. It is being prepared by the same method, by electrolysis. So by the time you get to calcium chloride, you have treated the ore up to this stage. Before you can, the final stage is when you are using the electrolysis. Okay, so we now know the sources and where we can get them from. Now, their importance. You see, we get calcium from calcium oxide, which is lime. So when you say slick lime or quick lime, we are not referring to the lime that we take you and Katrade. So what do you use the quick lime for? It is basic. So if you want to reduce acidity in the soil, you just take it and go and pour it into the soil. It is used to lower acidity of soil. A process called lambing and lakes affected by acid rain. So you could see that some places that we have a lot of industries there, a lot of carbonate, a lot of sulfur dioxide, nitrates, all have been released into the soil, in the air. So when it is raining, the rainwater dissolve the nitrate for it to form nitric acid. If it is sulfur dioxide, you form sulfuric acid. And this water will come and settle in the pool. So the pool that we're going to fetch water from is already acidic. So in order to neutralize it, you go and lime it by putting lime in it, and you just neutralize it to get the right water. How do you prepare quick lime? What we know is calcium oxide. When you have calcium carbonate and you heat it, it breaks down to give you calcium oxide and what carbon dioxide. So if you want to prepare slick lime, what is the same as? It's hydrated quick lime. So slick lime is hydrated form of quick lime. So you heat this, all the water will just vaporize. Then you produce your quick lime, what is calcium oxide. Now, calcium oxide, when you put it in water.
Say.
Yeah.
So the calcium oxide is an example of the quick lime. Now you are talking about
quick lime, calcium oxide. The common name is quick lime.
Okay.
So when the chemical formula for quick lime is CAO. What in chemical term we call it calcium oxide.
Okay. And then the second one, the calcium hydroxide.
Uh-huh.
One. Is also an example of the quicklime?
No.
Okay.
When you dissolve calcium oxide in water, you get your calcium hydroxide. What we see is what we go to the magazine and go and fetch. When we put it in water, we form the calcium hydroxide. Then you use it to paint our stones. So we call that one as a quicklime. But actually, the quicklime, which is sodium hydroxide, when you go to the magazine there, or you go to the shop, you see initially some people were using it to paint their houses, first coat. So you go to the paint shops, then you go and buy this in the form of solid marbles. You put the calcium oxide, you put it in the water for about, you soak it in water for about 3 days, 2 or 3 days. Then you form the calcium oxide. By the layman's name, or solution. I forming that white is and then I find a quick line.
Okay,
Right?
sir.
But actual sense, a quick line and a marbles now, but tunnel shop.
Okay, thank you, sir.
Okay. So what do you use calcium for? We now know its importance. So it is used in preparation of beryllium metal. It is a dehydrating agent for organic solvents. And even in the preparation of gases, don't you use it that it can absorb carbon dioxide? Or in water, when you are preparing, is it oxygen or when you are preparing, is it ammonia gas or whatever it is? It is used to absorb water. So it's called dehydrating agent. It is essential in living matter for teeth and bones. It plays an important role in our hearts, clotting of blood, and contraction of our muscles and nerves. Yeah.
With the dehydrating agent and then the dry agent, are they different? Because they are all removing water.
Drying agents. Yes, dehydrating agents is the same as drying agent, but the removal of water. Listen, we have hygroscopic substance and we have deliquescent substance. So the deliquescent substance, they're also removing water from the environment, but they will remove and dissolve in it.
Okay.
Right?
Okay.
Then the hygroscopic, they will remove and they will not dissolve in it. So if you want to use one to, let's say, as a drying agent, which one will you use? So both can be described as a remover of water, but both cannot be described as a drying agents. Have you got the explanation?
Yes, please.
Yeah, so deliquescents also remove water. Hygroscopic also remove water, but both are not drying it. So when you use drying agents, you are being specific. Whatever you want to remove the water and the thing will not become wet. But when you say dehydrating, you can dehydrate and that compound could be liquid. Is that okay?
Yes, please.
So calcium, what does it do? It serves a very good purpose for the body. It activates a variety of metabolic processes. So some of the metabolic processes in our body, without calcium, it will not take place. It activates it. Quicklime is used in metallurgy and the removal of all SO2 when fossil fuels burns. Slate lime for water treatment. Now, it's also acts as inhibitors. It inhibits calcium's reabsorption in the kidney, excreted in the urine. So we have what we call calcitonin. So is it not calcium what is going to do that? And what does the calcitonin refer to? It inhibits calcium ion getting reabsorption into what? The kidney, so that urine can excrete it. So thyroid gland, kidney. So it promotes for calcitonin. It promotes the deposition of calcium into the bones, inhibits osteoclast, and stimulates osteoblast. Inhibits calcium absorption by the intestines. Lowers calcium levels in blood. So what is the function of thyroid gland for calcitonin? So we are saying that it will activate some processes in the body. Is that okay?
Yes, please.
So this also is also in the elements. Strontium is also soft, silver white, yellowish metallic element that is highly chemically reactive. The metal forms dark layer when it is exposed to air. And this all that you see here. It occurs in as this celestites. There is no large scale use of strontium. It is extracted by electrolysis. The uses. So you know CRT. Do you know CRT? Cathode ray tube computers.
Cathode ray tube.
Yeah. Monitor front panels is used for strontium. Although strontium is not essential element and does not have any known biological role, its present in living organisms. It is present in living organisms. We don't know its main function there. It resembles calcium elements in its properties. Like it is taken up by preferentially located in the bones. Here, strontium can have both beneficial and deleterious effects in humans depending on the amount taken up. It is used to treat some infections like the bone problems, osteoporosis. Then another metal there is also barium. It is also soft, slippery alkaline earth metal. It is also very reactive. Barium is never found in nature as a free element, means it's very reactive. It occurs in barium carbonates with darites or the barytes. And this is how it looks like. It's extracted by electrolysis in a fused barium chloride. So either in the barium chloride or barium sulfate. Barium chloride, which is a salt, when taken into the body, is toxic. It causes serious deterioration of the heart, called ventricular fibrillation. Barium sulfate, which is insoluble, is not toxic. It's used medicinally to treat ailments in the digestive system, swallow. The dense salt, small amount, which is opaque to X-ray, is spotted at the point default. So in medicine, some people, when you're going to take X-ray, internally, especially in the intestines, they will allow you to swallow small portion. Where the problem is, it will be stuck there, and we take the X-ray and we need to analyze and find the fault there. So these are all examples. How do you use it? Barium is often used for sparkling plug electrodes and in vacuum tubes as a drying and oxygen remove agents, as well as fluorescent lamps, impure barium sulfide fluorescence after exposure to light. So some of the fluorescent tubes, we have them there. Then if you want to remove oxygen, it's also used. Its compounds are used by oil and gas industry to make drilling mud. So gas and oil industries, if they want to drill into the mud, they use it. Drilling mud simplifies drilling through rocks by lubricating the drill. So oil and gas industries, we are going to drill into the rocks to get the natural products. So it is used there. And how is it used? It is used as a lubricant. Drilling mud simplifies drilling through rocks by lubricating the drill. Barium compounds are also used to make paint, bricks, ties, glass, and rubber. Barium nitrate and chlorate give fireworks green color. Now, other metals, so we are other metals which does not belong to either group 1 or group 2 are aluminum, gallium, indium, tin, lead, bismuth. So what is the amount of aluminum in the soil? It's about earth crust, it's about 8%. It is also the third most common chemical element on our planet after oxygen and silicon. So aluminum, what we can use aluminum for? We have the saucepans and the rest. And those things that we use to, so the cover, the seal. And it's used in the automobiles, in airplanes, in machines, a lot of areas, aluminum pipes and all those kind of things. Aluminum is the third most abundant element in the earth crust. What forms are they? in the form of bauxites, aluminum hydrates. Then we have the berry, we have cryolites, then we have rhodium. All these types of aluminum ores. So in Ghana here, where you can locate these minerals, the bauxites, we have ayahuasca, so kibi. And this the sample of the bauxite. How do you manufacture aluminum from the bauxite? So primary manufacture involves 4 processes. And what are the processes? Extraction of the ore, that is the bauxite. Purification of the bauxite to pure aluminum oxide, which we call alumina. Then synthesize cryolites, aluminum fluoride to be used in the electrolytic reduction process. Then the final stage is the electrolytic reduction of aluminum oxide to aluminum. So before you can get aluminum, it should pass through 4 stages. First, you have to go and extract the bauxite from the earth. Then you have to purify the bauxite. Then you have to melt it with the cryolites, then pass it through the electrolytic reduction before finally you do the reduction of aluminum oxide. So let us first look at the extraction of the aluminum. So it is prepared from bauxite, which is frequently contaminated with silica, iron ore, or iron oxide, and titanium oxide. So we know the ore that the aluminum ore is called bauxite. And this bauxite contains silica, it contains iron oxide, it contains titanium oxide. But we are looking for our aluminum, so we have to purify it first. So the ore, how do we purify the ore? The ore is first heated with sodium hydroxide solution to convert the solution into a silicate. And we've now seen the chemical formula. So we assume that the compound contains the silicates. The compound contains the silica.
So we go watch till the class and
Yes.
like green inside.
Hello. I didn't hear what you said. Hello.
You then go, you will reach house, you see what them go do you.
You do what? Are you talking to me? Please, are you talking to me?
So the person is talking outside.
Oh, okay, sorry.
Why? Unless you want to put the further on.
So that illustration there. Now we want to we've gone for the ore, and we say that ore bauxite, the ore which we call the bauxite, We've already said that this bauxite contains the aluminum, but it is not only aluminum that is only there. We also have silica in there. So this is our silica. We have iron also there. We have other elements there. So we must purify
Sure, so
this.
you do this here.
So how do we remove the silica? We say that you should dissolve it in sodium
You know,
hydroxide.
see yourself again. Tracy.
So in the equation that you see, he has now taken off the sodium part and he has just represents only the OH side. So the OH side, who is the what? The important. So all the silica there will be converted to the silicate. So having to be able to remove the silica from the bauxite, and this is what's have been illustrated there. So when you come to the original material, this is what I just illustrated. So we have our silica. So we are dissolving it with sodium hydroxide. So the basic, what is making the substance basic is, so the sodium is not showing. So it is this side that is going to form with this for us to form of the silicate. The complete equation is not written, but we just showing how to remove the silica. So all the silica in the bauxite will be converted to silicates. So at the same time, aluminum oxide is converted to aluminate. So remember, in the bauxite, we have aluminum oxide also there. So when you add the sodium hydroxide to the crushed form of the bauxite, all the silica in it will be converted to silicates. And the aluminum oxide in it will be converted to what we call aluminate. And this, because we have the OH will react with it. So this is what we call the aluminate. So all the aluminum in it will be converted to the aluminate. Then we've already said that there is iron oxide also there. And tin is also there. So when you add sodium hydroxide, the iron oxide and titanium oxide will not be affected. So let's come back to this place. Our bauxite contains the aluminum oxide. Look at how the aluminum oxide is here. So don't you see the aluminum oxide? So this is what we call the bauxite. But within this bauxite, we have the silica, we have the iron oxide. Then we also have titanium oxide. So we want to purify this to get our aluminum oxide. So what we do, we first crush this, add sodium hydroxide to it. Sodium hydroxide will convert all the silica to silicate. Then all the aluminum hydroxide will converted to aluminum. But the sodium hydroxide will have no effects on iron oxide and titanium oxide. And this is what that is here, point 3. The iron oxide and titanium oxide are unaffected by this treatment and are fitted off. So we've crushed our rock. We've now dissolved it in sodium hydroxide. So we are now going to get some of the compounds to be in solution. So what compounds are going to be in solution? The silica will contain silicates, aqueous, aluminum oxide will convert it to alumina. Then the iron or iron oxide and titanium oxide will not dissolve. So they will remain as a fixing in this solution. So we can now filter off the iron oxide, titanium oxide. So here, the first stage, we've now been able to remove the iron oxide and titanium oxide. So what remains in the solution is going to be the silica or the silicates and the alumina. So what the fixate, the solution is then heated with acid to precipitate insoluble aluminum hydroxide. So our solution that we have obtained now containing the silicates and
send me this one. Then this is R actually. This is the Newtonian surface tubes. Then this is
what
chemistry. Justice. That one be IWC. IWC. This one there, I know saying they go on.
The Albert.
Can I continue?
Do they inside? I know they go. Okay, so like maybe them see the thing late. Wait, what's again? UCC. The madam.
Sir, please, you can continue. But the one talking is talking outside the group.
Okay.
So apart from that, then
that became it.
Then
so now
he's the coordinator. He's the coordinator. He's the one recording the lecture.
Okay, no problem. So what we are
I suggest if they can mute off, if they can mute their microphone.
This one, hopefully.
If I can,
I think
I mean the coordinators. I suggest they mute their microphone.
What planes you have?
Okay.
Actually, by this time, I create a study center. They think of how to reach out.
Saturday.
Please.
Maybe he's not aware that
the one who is monitoring. Okay, let's continue.
Okay, cool.
Okay, so we now know we are in the process. We have now been able to remove the silica now. And we have also been able to remove the iron oxide and the titanium oxide. So the first one, how did we remove? The first thing that we removed were two, the iron oxide and the titanium oxide. How were you able to remove it? We first dissolved the crushed bauxite in sodium hydroxide. Then the sodium hydroxide will dissolve the silica into and form the silicates. And all the aluminium oxide also become converted to the
aluminium. Just they go individually, but they do have a.
So then they use the computer.
Use the mouse.
This one will not have any effect on the iron oxide.
If, say, for example,
also have no effect on the titanium oxide. the titanium
That one to the second phone. That's why we made
iron
this.
oxide to be filtered off from
Second
the
phone or then they
so
communicate.
now after you've done the first filtration, our filtrate now contain what? The
And then we also
silicates
attempt password.
and aluminum.
I
So
go then me
what do you do now? You want to get
I go pick the phone and you connect you something. Or
aluminum.
maybe you wait till for
So
closer and then you
you
put the thing for the
add
what's up for
acid
you
to
see
the
amount now.
solution, and that acid
Maybe
will
pass
make the alumina insoluble. So it will form aluminium hydroxide. So the aluminium hydroxide is now insoluble. So you perform your second filtration. So the solution is then heated with acid to precipitate the insoluble aluminum hydroxide. After that, you have to separate the aluminum, what is insoluble, from what? Your silicates, what is soluble. So you perform it to get your aluminum hydroxide. So the aluminum hydroxide now becomes the residue. Then just after you have done that, you heat it, and the hydroxide part will just vaporize for you to form the aluminum oxide. What is Al2O3? Aluminum oxide means it does not contain any water as impurities because we've now heated it. So after you've now heated your residue, what is aluminum hydroxide? You obtain the aluminum oxide, and you are not done. So what you have now obtained, you are now going to perform another reaction with it. We are going to put it, melt it, and use electricity to separate your aluminum from the oxygen. So this is what you get here. So you make it into a solvent form by boiling it at a temperature of 20-45 degrees Celsius in electrolysis process to produce your aluminum. So during the electrolysis process, what is going to happen? All the oxygen are going to move to the anode. They take electrons there and they become oxygen gas. Then all the aluminum will move to your cathode. Then what is going to happen there? They are going to gain electrons from the cathode and be reduced to aluminum metal. So they will sink into the bottom and drain from time to time. Oxygen will form at the anode and aluminum will form at the cathode. So you will see, because of the cathode there, we have carbon there. So you also observe carbon monoxide being escaped. And we call that as Hall process. And this is the setup. So this is when you are separating the thing. So you see, you have your aluminum oxide. It's in the form of solid. You need to melt it. So you melt it with this compress, Na3Al(F6). You heat it at the highest temperature. Then you have your electrodes. You have the anode, you have the cathode, then you have the electricity source. Then you have your carbon lining inside. That is from the cathode. Then you have the outlet where the aluminum is going to come from, or to be allowed to pass. And the whole process is what we call Hall process, also called Hall Harrod process. Then we have another process called Bayer process. So here is how the setup is. Here is the crusher. So can you see that we are now putting the aluminum, the order contain aluminum, and it will be crushed here. That's why we call here crusher. Then when it is crushed, it's descend into the digester, where you have your sodium hydroxide on the line. Then you know what has been formed here, because the sodium hydroxide has converted the aluminum here to aluminum oxide. Then the silica has also been converted to silicate. But the iron and the titanium oxide are not converted. So they move to the filter where the filtration takes place here. So it moves on. Then after filtration, your alumina, you are going to add acid to it to precipitate the alumina to aluminum hydroxide. Then after the aluminum hydroxide has been produced, what is going to do, that's why you see here heating, what we call calcination. So you heat it, then all the water component in the aluminum hydroxide will just vaporize. You form your alumina. Then the alumina is the L2O3. Here is where the thing is now going to pass through the electrolysis for it to obtain the aluminum. So another way of illustrating the routine: oxide, crusher, milling. Then pressure vessel. You add your sodium hydroxide, you filter to get the red mud, then you get sodium aluminum hydroxide, cooling crystallization, and you get the system. Then you've now heated it in the oven, getting aluminum oxide, and brings you to this last stage. Okay, so all these are the processes. So we want to also recycle the aluminum. So about 3 billion pounds of aluminum cans and fuels are discarded annually. So if you don't want to go and mine the bauxites, you can also recycle the cans. To also get our aluminum metal and go and reuse it. Look at the aluminum cans. After you use them, what do you use them for? You throw them away. So we can recycle to get our aluminum back and go and use it again. So about 3 billion pounds of aluminum cans and foils are discarded annually. So preference, what we are looking for is aluminum. So non-toxic. Aluminum is not toxic. It's odorless. It is tasteless. It is very light in weight. The thermal conductivity is very high. With this means these best environmental solution is of recycling them. So from the whole process, the energy required for the production overall, you are getting the aluminum oxide to go through the same procedure to produce our aluminum once again. So all these the manufacturing, so the manufacturing products new scraps, product usage, scrap separation, collection, and all those kind of things. For the recycling. Properties of aluminum. It has a low density of about 2.5 grams per centimeter cube. High tensile strength and malleable. Excellent conductor of electricity, about 65%, that of copper. Preferred because it is cheaper and lighter than copper. It is widely used in high voltage transmission lines. It's cheap use in construction of aircraft, alloying with small amount of copper, magnesium, manganese, and silicon. Aluminum alone is too weak and soft to withstand the strain. It is non-toxic and therefore used as cooking utensils. It does not react with water, but with acid and strong bases. So if you have aluminum pan, don't go and add acid into it or base, it will react with it. It readily forms when the oxide is exposed to air. So when aluminum is exposed to air, it's reacts with oxygen thin layer to form the aluminum oxide to coat the surface. The firm coating on it prevents pollution. So this accounts for inmates. That's why aluminum finishes that prefer use in the coastal area. It helps in rusting. It's preventing rusting occurring. So its heat of formation is about negative 1670 kilojoules per mole. The high energy makes it suitable for use in solid propellant for rocketing and space shuttles. It has a great affinity for oxygen. The termites reaction has temperature approaching 3000 degrees, used for welding of steel and iron. So in the welding, welders, they use it to weld steel and iron. Hydrolysis of aluminum chloride. So aluminum chloride is very soluble in acid or so in water. So when you have aluminum chloride, you put it in water, you form your aluminum or hydroxide, what is solid, and aqueous, what is aqueous. Means when you have the aluminum hydroxide, you can, when you have aluminum, you can dissolve it in HCl, and that's one will produce hydrogen gas. Aluminum oxide hydroxide is described as amphoteric because it reacts with acid, and it can also react, it can act as an acid, and it can also act as a base. So in the acid, aluminum is dissociated to give you aluminum 3 plus and the water. And in the base, you shall form aluminum hydroion. It forms a lamp. General formula is this. Aluminum sulfates and alum. And alum has a general formula of M1, M3, they are all metals, sulfates, and water. So what are the benefits of alum? You know, it's natural remedy for pimples. People use it to control pimples. Alum works as natural deodorant, used for aftershave, treats canker sore, get rid of athlete's foot, helps to purify water. So people will go and buy alum in the market, and when they have dirty water, they put it in there, and all the dirt will settle at the bottom. Some aluminum powder benefits. Other fats, natural remedy for pimples, used for shaving, treats canker sore, reduces wrinkles, works as deodorant, helps to purify water, reduces head lice, get rid of athlete faults, reduce head lice, and it is natural antiseptic, anti-inflammatory, antibacterial properties, and natural astringents. So reduces head lice, makes heels soft and smooth. So uses of aluminium, about 26% for building. In transport area, 36%. Packaging, 17%. Engineering, and 14%, and others. So nowadays, the aluminium. So where can it be? At the surface of the skin, acupuncture. So they put it on, so people use it as medicinal distance. So they use it in the acupuncture darts, and they can sweat that. So you see this Chinese, they use this thing to punch, needles to punch the skin. So what are they doing? They are introducing it into the system. And these are the areas that I can go to. Acupuncture gland, sebaceous gland, sweat gland, and all those. So these are the areas that they are used for medicinal purposes. So we have the medicinal, diets, guts, lungs, aerosol, exposure, tropical, skin, noise, and all kind of things. Okay, so we are now done with all the metals, important metals that are in the main group elements. We've now captured the group 1 elements, the group 2 elements, and we have taken one particular element in group 3, that is aluminum. Now the rest, you have the semi-metals, non-metals. In the non-metals, we have the halogens, we have the noble gases, and other non-metals. So let us also look at something here. We can group elements into some areas. We have D block elements, we have S block elements, we have S block elements. So these are the other metals that we have considered. So here, for the gallium, it's also part of the group 3 elements. It's also soft, silvery metal at standard temperature and pressure. It is, however, in its liquid state, it becomes a silvery white. It also undergoes the same reactions with air. It forms the oxides. With water, it does not form the hydroxides. It forms when it reacts with water, it will give you the oxide and produce hydrogen gas. It's also reactive acids, and it's also reactive grease. So it's also described as so amphoteric. What do you use the gallium for? Gallium arsenide has a similar structure to silicon and is useful to substitute silicon. It is useful. Silicon substitute for electronic industries. It is important component of many semiconductors. LEDs. LEDs. We can also form the gallium nitride, which is a semiconductor. Its particular property is that it makes very versatile. It has important uses in blue-ray technologies. Gallium readily alloys with most metals. It is particularly used in low melting alloys. It has a high boiling point. It makes it ideal for recording temperatures that will vaporize at thermometers. Biological role. What role does it play? Gallium has no known biological role. It is non-toxic. Then we have indium, which is also the softest metal that is not an alkali metal. It is silvery white metal that resembles tin in appearance. It has a melting point higher than sodium and gallium, but lower than lithium and thin. Properties. It's form oxide with air. It form oxide with water and release hydrogen gas. It also reacts with acid and base. So it is also as amphoteric. Uses of indium. It also has no biological role. In small doses, it is said to stimulate metabolism. Indium has no biological role. In small doses, it is said to stimulate metabolism. It is rare to encounter indium substances around us. All indium compounds will be regarded as highly toxic. Indium compounds damage the heart, kidney, and liver, and may be teratogenic. Insufficient data are available on the effect of the substance on human health. Therefore, most care must be taken. Environmental effect of indium. Since indium is not widely dispersed in the environment, it poses no threat to land or marine life. Environmental effects from the substance have not been investigated, so we don't have much information about indium. Thallium. Thallium is a very gray post-transition metal that is not found free in nature. When isolated, thallium resembles tin, but discolors when exposed to air. Poison chemistry. Thallium sulfate is very poisonous. Thallium poison, easy to diagnose and treat if you think of it. So, available overseas or right poison. So, what are the symptoms? Hair losses, severe brain damage, red skin, mental changes. If there's not enough time for the hair loss, and unsuspected pathogenic may miss the thallium metal. Oral Museum blue authorities. Reactions of thallium. It also reacts with oxygen. It reacts with acid and it reacts with base. What do you use it for? It's limited as it is toxic element. The thallium sulfate was employed as a rodent killer. It is odorless and tasteless, but household use of this poison has been prohibited in most European countries. Most thallium is used by the electronics industry in photoelectric cells. Thallium oxide is used to produce special glass with high index of refraction and also low melting glass that becomes fluid at about 120 K. An alloy of mercury containing 8% thallium has a melting point 20 degrees Celsius, lower than mercury alone. This can be used in low temperature thermometers in space. Biological rule. Thallium is also known, has no known biological rule. It is very toxic and it is very toxic. And there is evidence that the vapor is both teratogenic, as they said the development of an embryo or fetus, and carcinogenic. It can also displace potassium around the body, affecting the central nervous system. Then the other one there is tin. Tin is very silvery metal that's characteristic as a faint yellow core. Tin, like indium, is soft enough to be cut without much force. Properties. Tin is soft, malleable, forms compound with oxidation state of +2 or +4. Tin 2 compounds called stainless compounds are generally more aromatic and reducing. Tin 4 compounds called stannous compounds are more covalent and oxidizing. Tin, the principal ore is tin 4 oxide or cassiterite. It is prepared by reducing tin 4 with carbon at elevated temperature. And this is how it is. So we have the tin 4 plus carbon, and it will reduce the tin. There are 3 allotropic forms of tin. These are gray tin, white tin, and gamma tin. So gray tin is 13 degrees Celsius, white tin 160 degrees Celsius, and gamma tin converting temperature. Tin 4 oxide is this. Reaction of acid. Tin reacts with acid to form tin chloride and production of hydrogen gas. It's also, so if it's a reaction of nitric acid, it will give you in 2 tin oxide and NO2 and hydrogen gas. It can also react with sodium hydroxide and potassium hydroxide. So it's also been described as amphoteric. Tin is amphoteric shown in the equation here. Reaction of chlorine, it's a reaction of chlorine molecule gas to give you tin chloride. Unlike carbon and silicon, tin forms only SnH4, H2H3, they are unstable. So you can't form this in that. Alloys of tin in bronze, tin is 20%. Soft soda, tin is about 33%, and filter. So bronze is made up of tin and copper. Soft soda is made up of tin and lead. And pewter is made up of tin, copper, smooth tin. Tin poisoning refers to the toxic effect of tin and its compounds. Cases of poison from tin metal, its oxides, and its salts are almost unknown. So that's why it is used to canon a lot of things. Tin poison refers to the toxic effect of the tin and its compounds. But so far, we've not come across causes a tin oxide and tin salts. So all these things are made up of tin containers. So use as a soda to red metals, use as utensils, use as refill sheets, tanks, toothpaste containers, tin bulbs, batteries, battery cage, and a lot of them. Then the lead. Lead is heavy metal that is denser than most common materials. Lead is soft and malleable and also has a beautiful melting point. When fresh lead is slippery with hints of glue. It tarnishes to a dull gray color when exposed to air. So all is lead. Lead is chief ore is galena. Extraction is done by roasting of the ore. So you roast the ore, you get it. The oxide is then reduced in the last furnace with coal. Both tin and lead are less electropositive, hence they are best prepared by chemical reduction rather than expensive electrolysis. Note this one very well. Tin and lead are less electropositive, hence they are best prepared by chemical reduction rather than expensive electrolysis. The two compounds are more stable than the four compounds because of the net effect. Except lead, acetate, and nitrate, most lead compounds are insoluble. Uses to gray to glass ceramic vessels. Lead oxide, white pigment in paints, and protective cells to nuclear chemists, X-ray operators, and radiologists. Protective shell is used to protect repair lead storage batteries.
So say,
Yeah,
so please, all the white paint contains lead.
yeah. White paints, white pigments in paints. You say white pigments in paints.
So it means that it's only the white paint that contains that lead, because
Yeah,
other paints is red and other things they do not
but you
contain.
see in the manufacture of paints, they mix various colors. So the color will not be maybe pure green. They have mixed various colors, including white, that are giving them that color.
Okay.
So unless you say maybe the pure blue that has no pigment of white in it, they also go to those who manufacture the paints. They don't you say that we have secondary colors.
Yes, sir.
So for the primary colors, it is the color itself. But the secondary colors and the complementary colors, it is a mixture. So therefore, some white pigment color could be there, but because it has mixed very well, you may not see it. So if you want to bring that in, make it primary colors.
Okay. So it means that other colors also have that white pigment. That is the lead.
Now, what I'm saying is, if the thing is not primary color and it's the secondary color, it could be quite mixing with maybe blue. So when you mix white color with blue, it will give you another color.
Yes, sir.
So we are missing two primary colors.
Okay.
Yeah, okay.
Yes, sir.
So the second color that you are going to get contain the white pigments in there.
Okay. I see.
I hope you understood my point.
Yes, please. Thank you.
So we have lead batteries. We have lead pipes. This time is found. Because of lead is poisonous, so you don't use it to transport water again. Then we have the lead wire, lead sheets for various things. So end use of lead, look at this, for batteries, for raw excretions, for ammunition, for pigments, for cable sheeting. So we have lead batteries, lead is toxic, lead bullets, especially the farmers who go on hunts. So they have that bullet. Lead has been used in petrol, water pipes, paints, and soda, but its use is now restricted due to its toxicity. Currently, the largest commercial use of lead is in the lead acid batteries, which are found in cars. So initially, we are using it in petrol. We are using it to transport water in lead pipes, in lead paints and or soda. But we are being warned that it is very toxic. So anything that can poison the human system, we should not use lead to transport it. Then car batteries. Then it is used in other current uses of lead include bullets, organ pipes. So you've seen organ pipes, weight belts for driving and table shifting. Lead has known beneficial function in human metabolism. On the contrary, it is toxic and has been known. Source of lead injection. Tetraethyl lead is used as anti-knocking agent in gasoline to increase performance. So in the lead petrol, you see now they have given the grade. We have 91, 95. So lead tetraethyl lead is added to the petrol to use as anti-knocking agents. And when you increase the return number, it increases the performance of the petrol. Leaking of sweat, white paints by children and animals. So how can we inject lead into our body? We can inject lead into your body through petrol. Don't you see that some people, when their car runs short or the magazine, when they are repairing their cars, the engine is not starting or the pump is not functioning very well, you just suck some of the petrol into their mouth. If that petrol contains the anti-knocking agents, that is lead tetraethyl, When you use your raw hands to touch it or you suck it into your mouth, you are injecting lead into your system. Then children also licking of sweat. Licking of sweat, white paint. The white paint, so licking of sweat, white paint by children and animals. So paint no one with a white paint probably everyone or metal one. So sometimes you see children licking it. The sweater comes. You are introducing lead into your system. Whiskey drinkers consume quantities of lead contaminated moonshine. Eating or drinking from improper lead based earth. Eating or drinking from improper lead based earthware. The earthware, then soldering pipes joints. Part of fire, because it's air metal, we use solder to join it. So it may contain some amount of lead. And this is how human beings or animals inject lead into their system. The effect of lead. When it's accumulated in the humans, it leads to lead poisoning. So how is it caused? It is caused by lead-2 ion or tetra lead through inhalation or injection. When you get lead ions, it inhibits enzymes that catalyze the reaction of biosynthesis of hemoglobin, leading to anemia. Lead is more poisonous. This tetrahedral lead is even more poisonous than lead-2+. The former is converted to the hydrocarbon group. It's non-polar. This makes it possible for it to move across membrane layer more than uncompressed lead iron. So symptoms of lead poisoning: 1. Anemia, brain damage in children, central nervous system impairment, impairs kidney functioning. How do we treat lead poisoning? It is treated with chelating agents such as ETA, diethylene diamine tetraacetate, and 2,3-diamine captoprofenol for BAL, British anti-Lewis sites. Identify the formula and mechanism for the eradication process. Afternoon. Me online new basis. I'm a friend and a family. It's in my feelings. So when we look at this picture, there is symptoms of lead poisoning. the areas that it can attack. Then other method in group 3 is Smith. It is brittle, crystalline, white metal with a slight tinge. It has a variety of uses, including cosmetic alloys, fire extinguishers, and ammunition. It is probably best known as main ingredient in stomach ache remedies such as pector bismol. So it's used as a drug. And these are the various uses. Used in cosmetics, used in fireworks, used in medicine. The reactions is also reacts with air to form the oxide. It also reacts with acids. And it's an hydrolysis reaction. Then we have some metals called candidate metals, and they are the transition metals. But this one is about main group elements. But you must know when we say candidate metals, we are referring to transition metals. So the transition metal that we look at as copper. Copper is soft, malleable, and water. Metal with very high thermal and electrical conductivity. Fresh exposed surface is used to prepare do a lot of things. Biological view of copper. Copper is an essential element. On average, men use around 1.2 milligrams of copper a day to help enzymes transfer energy in the cell. Excess copper is also caused genetic diseases such as Wilson's disease and Menkes disease can affect the baby's ability to use copper properly. Unlike supposed to use iron and hemoglobin to transport oxygen around their bodies, some crustaceans use copper complexes. So, I want to introduce something to you now. For the metals we are done with the main group remaining metals. The material is telling us that we should at least look at the chemical metals, some of them, very few of them. But I want to ask you look at some type of classification. So when you look at this, we call the first group as alkaline metals, then we have second group as alkaline earth metals. Now, on the periodic table, I also show you where transition metals are located. So we have the first transition metal, second and the third. So we have the lanthanides and the actinides. Now, transition metal is also known as tannate metals. So copper, in natural sense, is not part of transition metals unless it's ionized to about copper 1. When you come to the actual transition metals, for the first one, what makes them to fall within, they should not have their d orbitals fully filled. So, but because we've not gotten there, let us consider copper as one of the transition elements or transition metal. So copper, the nature of copper is soft, malleable, and ductile metal with high thermal and electrical conductivity. The freshly exposed surface of pure copper has a pinkish orange color. And this how it looks like. Now percentage there. So other where you can find the most. This is historically, copper was the first metal to be worked by people. The discovery that could be hardened with little tin to form the alloy bronze gave the name to the Bronze Age. Traditionally, it has been one of the metals used to make pens, along with silver and gold. However, it's most common of the three, and therefore the least valuable. All US coins are now copper alloys, and gun metals also contain copper. Most copper is used in electrical equipment such as wiring and motors. This is because it conducts both heat and electricity very well and can also be turned into wires. It also has uses in construction. For example, roofing, plumbing, industrial machines such as heat exchangers. Copper sulfate is used widely as an agricultural poison and as an herbicide in water application. Copper compounds such as ferrous solution are used in chemical tests for sugar detection. Biological rule. Copper is very essential to elements to humans. In adults human needs about 1.2 milligrams of copper a day. And what is the function? It is going to help enzymes transfer energy in the cell. By excess, we can cause it. So this Merkin's disease, dietary brain, small intestines, kidney, skin, and hair color. So how are they used? For construction was 43%, machine 7%, consumer product 10%, transportation equipment 20%, and electrical and electronics 20%. The next important element is silver. Copper is not
Say,
yeah,
please, can we know some of the sources of copper?
the
Since
the ore.
yeah,
So you remember the ore, the bauxite,
yes,
those kind of things. So they are obtained from the ore.
okay, okay.
Since we are not taking it completely, that's why I'm not saying a lot of things about it. It's not even reactive. So you know it. That is why it's used as a ornament. Copper, gold, and silver. They are not reactive. So we come to silver is also salt, white, lustrous. It's also part of transitional minerals. It exhibits the highest electrical conductivity, thermal conductivity, and refractivity of any metal. What do you use this for? Ferrous silver contains 93.5% silver. The rest is copper or some other metal. It is used for jewelry and silver tableware, where appearance is important. Silver is used to make mirrors, as it is the best reflector of visible light known, although it does not tarnish with time. It is also used in dental alloys, solder and brazing alloys, electrical contacts, and batteries. Several paints are used for making printed circuits. Silver bromide and iodide were important in the history of photography because of their sensitivity to light. Even with the rise of digital photography, several salts are still important in producing high quality images and protecting against illegal copying light sensitivity glass. Silver has antibacterial properties, and silver nanoparticles are used in clothing to prevent bacteria from digesting sweat and forming unpleasant odors. Silver threads are woven into fingertips and gloves so that they can be used with touchscreen phones. Biological rule. Silver has no biological rule. Chronic ingestion or inhalation of silver compounds can lead to condition known as agrilia, which result in grayish pigmentation of the skin and mucous membranes. Silver has antibacterial properties and can clear lower organisms quite effectively. And this, how do you use electrical and electronics 35%, pens and metals. Then we have photography, jewelry and silverware. So we have here all these things. Then we have the food, white, slightly reddish, yellow bone soft, malleable, and butter metal. And these are the things we can use food for. So arthritis, fuel additive, and oceans. Both compounds were used to treat arthritis. Side effects and newer drugs have reduced this use. Both leaf and flakes are edible and added to a range of products, including cakes, pastries, and butter. Large quantities of gold are dissolved in oceans, but too low a concentration for economic extraction. So some selected transition method that we have looked at is gold, silver, copper. Then there are zinc, cambium, and mercury. They are all carnage metals. So now when you say carnage metals, you know some of them. They are what? Copper, silver, gold, zinc, cambium, and mercury. So we have zinc, cambium, mercury. These metals resemble the alkaline earth metal because they have their electronic configuration NH2. That's the difference in chemical properties is due to number of electrons next to atomic shell. Calcium shell, all those kind of things. D orbitals do not share after electrons effectively from the nucleus. This accounts for an increase in this one. Now, I've not taught you this thing, so you let me speak to you. I'll come back to them. So why is it used? Also, cambium uses electrons less readily than proton, boron, making the former less reactive. So this is their shape and movement. So zinc main or is a zinc sulfide. What we call spilarites or zinc main. And this now the structure is like. How do we extract it? This is obtained by roasting sulfide in air to form oxide. So we have zinc sulfide. When roasted in air, you get zinc oxide. Then zinc oxide, we combine it with carbon. We call fruit bubbling, carrying sulfide or air particles. And this side, it's like compressed air, sulfide oil particles. Water containing pipe oil when you have the gas. So this is how it is done. And this is how what is there, what has been simplified as this. So cambium is about 1,000 as abundant as zinc and is present in some amount in most zinc ores as cambium sulfide. So this cambium sulfide is obtained from smoke dust emitted during purification of zinc by distillation. Cambium is more volatile, means fluids. Both are silver metals. Zinc is hard and brittle. Cambium is soft, can be cut with knife. Their oxidation state is class 2. They react with strong acid to produce hydrogen gas. Zinc and carbon oxides are formed by direct condensation oxygen molecule. Zinc is amphoteric, cambion is not. The intense cambion towards basic solution is useful for protein methods used in alkaline media. What do you use as an formation of grass? So grass is made up of zinc and copper. Galvanizing iron in electrolysis using iron cathode in the zinc melting. Zinc sulfide has barren surface as white pigment in heat, so it's also in heat. It's not toxic and it produces lead. Zinc sulfide emits light, non-struck X-ray or U presence in screens of TV, oscilloscope, and X-ray fluorescence. It is essential element in living matter, aids in the activity of a number of enzymes, as carbonic anhydrase, which catalyzes dehydration of carbon dioxide. It is required for numerous processes in your body, including gene expression, enzymatic reaction, immune function, protein synthesis, DNA synthesis, wound healing, growth, and development. So you know the importance of something in the system. It is essential element in living organism. Based in activity of a number of enzymes as carbonic anhydrase, which catalyzes hydration and dehydration of carbon dioxide. It is required for numerous processes in your body, including gene expression, enzymatic reaction, immune functioning, protein synthesis, DNA synthesis, wound healing, growth and development. Zinc is an essential mineral that your body does not make on its own. It aids growth, DNA synthesis, immune function. So our body cannot synthesize zinc. Zinc is an essential mineral that your body does not make on its own. Zinc is essential for cell growth and division, immune functioning, enzyme reaction, DNA synthesis, and protein production. Zinc may be effective reducing inflammation, boost immune health, reduce your risk of age-related diseases, speed wound healing, and improve aging symptoms.
Tetraethyl lead
Yes,
is used as anti-locking agent in gasoline to increase performance.
Yes. Let's discuss this before we continue. When we were treating hydrocarbon last semester, I remember I said heptane. Was it heptane or pentane was used in anti-locking for gasoline? Do you remember?
Yes, madam. Yeah.
So someone should discuss or explain the sentence for us.
what sentence? Yes, what sentence? Who was speaking?
Sir, please continue. The person has left the group.
Okay. So zinc may affect effectively reduce inflammation, boost immune health, reduce your risk of age-related diseases. So you know the age-related diseases, speed wound healing, and improve aching symptoms. Risk factors for zinc deficiency include insufficient dietary intake, poor absorption, alcoholism, genetic mutation, and old age. So if you don't have enough zinc in you, you age faster. Zinc occurs naturally in food like shellfish, meat, poultry, and dairy, and is added to other foods such as breakfast cereals. And wheat flour. Are you there?
Yes, sir.
Hello. Yeah, the thing just went off. Okay. So you are saying zinc occurs naturally in foods like what you've already mentioned. Zinc toxicity may cause diarrhea, headache, abnormal cramps, abdominal cramps, and reduce immunity. Most people can obtain their daily dose of zinc through diets alone. Signs and symptoms
So,
of zinc.
so excess intake of zinc can also be a poison to the system.
Yes, zinc toxicity may cause diarrhea. So the overdose, you see, everything God has created has a limit. So overdose can cause diarrhea, headache, abdominal cramps, and reduce immunity. Most people
Okay.
can obtain their so signs and symptoms of zinc overdose: nausea and vomiting, stomach pain and diarrhea, flu-like symptoms, low blood HDL cholesterol, changes in your taste, copper deficiency, frequent infections. So that's why when we are sick and we go to hospital, they ask you to perform a lot of tests. So what they do is what they will suspect, they will ask you to go and have tests on it. Zinc poisoning is potentially life-threatening condition. It is important to seek medical help immediately. We are no safe. Boost your metabolism. Making small lifestyle changes will make it your routine to increase your metabolism. Having a high metabolism can help you lose weight and keep the zinc off, while also giving you more energy. Zinc oxide used as pigments in paints, cements, and treatment of rubber and skin diseases. How do you prepare zinc oxide? You have zinc solid, you expose it to oxygen and form your zinc oxide. Or you have your zinc nitrate, you heat it and you break to zinc oxide, nitrogen dioxide, and oxygen. The same way, when it's carbonate, you heat it and it's also decomposed. So they use this galvanizing, die casting, brass and bronze, bronze and chemicals and other. So these are the uses and what we can obtain from it. Use of cambium. Cambium. The major use is electroplating of iron. So you use the cambium as an anode and steel as cathode. Like many heavy metals, it is highly toxic. Symptoms of cambium poison, hypertension, anemia, kidney failure. Mechanism of CB poisoning is when respiratory system, pneumonia, and destruction of mucous membrane, kidney, proteinuria, kidney stone, granular, and tubular damage. Serious. So reproductive system, testicular necrosis, estrogen-like effects, affection of steroid hormone synthesis, skeletal system, loss of bone density, and mineralization, vitality diseases. Source of cadmium, electroplating industries, discharging waste into water bodies, wearing of automobile tires, degrades. So you've seen a wearing of automobile tires, degrades cambium oxide or zinc oxide, tobacco smoking. When we come to mercury, it is the only metal that is liquid at room temperature. Principal or mercury sulfide, cinnabar, very small in the earth crust. It is extracted by first concentrating by floating and the roasting in the air to yield mercury oxide. So mercury sulfide roasted in air will give you mercury oxide. The oxide is then decomposed to yield mercury vapor. And this is how the process is done. This is a machine. Properties of mercury. It is bright and silvery, dense liquid, freezes at negative 38.9 degrees Celsius and boils at 35 degrees. boils at 357 degrees Celsius. It dissolves many metals such as copper, silver, gold, and alkaline metals to form amalgam, either liquid solid, except iron, hence mercury stored in iron containers. So you've seen how it is. Those who are in the Galamsey sites. So when it comes in presence of gold, it will dissolve it, form an amalgam of it. Metals are generally more reactive than the amalgamated states in sodium. Mercury reacts with sodium with water. Amalgams are useful as mild reducing agents in organic synthesis. Example, Clemenson's reduction. So organic chemistry, we see this. So Clemenson reduction is zinc in mercury, presence of ECl. Zinc amalgamated with zinc. Unlike zinc, cambium and mercury has oxidation state of +1. Mercurius +2, mercury. It does not react with water and not decompose by ECl because it is positive reduction potential. Many mercury 2 salts are insoluble. Thanks to the rain and weather, it cannot pollute the environment. Mercury 2 has greater tendency to form covalent bonds with fluorine, but hydrogen mercury fluoride is ionic. It is capable of forming metal-metal bonds. Uses of mercury in thermometers. It has a large and uniform coefficient of volume expansion. In barometers, because of its high density. Sodium electric gadgets, thermostats, because of its high conductivity and because of its fluidity. As cathode in electrolysis for production of some elements. Amalgam pure metallic mercury is not poisonous. Ingestion produces non-noticeable ill effects. So uses dental amalgams, the thermostats, auto switches, light switches, fluorescent lights, thermostats, batteries, and appliances switches. So mercury, when volcano is erupted, it produces mercury dust. So this mercury comes to meter mercury, then it comes back to the sea. Salmon, crop, oysters, take them. Sharks inputs. So sharks eat this mercury. Sharks are airborne polypats. Food chain. So mercury level advice for consumption. Eat only few times of eat a few per week, unlimited. So you see how mercury is coming back into the system. Coal plants also release mercury. Marine water release mercury. Then volcanoes eruption also release mercury into the sea. Then these small fish get them into their system. Whales, then salmon, hullocks, oysters also take them. Then clams this go and need them, sharks and other fishes also take them. And look about the amount. So salmon, pollock, oysters are only unlimited. So if you want, you eat now only few of this. So what are the symptoms? That's when human beings has poisonous level, headache and fatigue, respiratory diseases, cardiovascular illness, gastroenteritis, nausea, cancer, skin irritation. So metals which have been put under, they are being classified as heavy metals are lead, cadmium, mercury, and arsenic. Mercury poses a particular risk to children, infants, and fetuses. Impacts include nervous system damage and developmental defects like reduced IQ and mental retardation. Cadmium ingestion can cause stomach and intestinal ulcers, anemia, and stomach ulcer. Frequent inhalation can cause asthma, wheezing, and lung cancer. Selenium. Selenium is used in many body functions, but deficiency or excess can be bad for one's health. Excess intake of selenium can result in a host of neurological effects, including impaired vision and paralysis, and even death. Lead exposure can result in brain swelling, kidney disease, and vascular problems, nervous system damage, and can lead to death. It is acceptable that there is no safe level of lead exposure, particularly for children. Arsenic. Ingestion of arsenic can lead to nervous system damage, cardiovascular issues, and urinary tract cancers. Inhalation absorption through the skin can result in lung cancer and skin cancer. Boron. Inhalation of boron can lead to over the short term eye moves and throat irritation. Ingestion of large amount of alpha can result in damage to the testes, intestines, liver, kidney, brain, and eventually lead to death. So other toxicants contain antimony, cadmium, molybdenum, and thallium. So, my dear students, I think we shall pause at this place so that you, when you meet again, you begin with non-metals and metallos.
Okay, sir.
So thank you for engaging me around this festivity. I
Thank
wish
you.
you a Merry Christmas.
Same to you.
Continue of your time to listen. I will look for more questions. If our questions will be structured around this topic. So Until we meet again, let's say goodbye to everyone.
Goodbye, sir.
Bye.